All right, if we have inverse functions, what do we know? Chris, give me one thing that your pod talked about of the three.
You simply find it, you switch back.
Okay. To find it, we switch X and Y. That's probably what sticks out the most to you about finding inverse functions. Okay. Maddie, give me something else that Pod 1 talked about.
Isn't it a reflection of how the graph?
Yes. Graphically, we have a reflection about the line y equals x. Okay. And then really numerically, the best way to describe it is we switch x and y. Okay. So I want to talk about some of the pre-calculus concepts that we know about inverses before we get into what we can do with derivatives and inverses. Okay. So I don't want you to write this down. Okay. I don't want you to write this down. But I want to remind you that we proved that functions are inverses of each other by doing the composition, right? A square root and a square, they undo each other, okay? Because they're inverse operations, right? So if we have an inverse, when we plug it in, we should be left with x, okay? A cubed root and a cube are going to undo each other. You're just going to be left with x, okay? That's how we prove we have functions that are inverses of each other, okay? Like Pod 1 mentioned, inverses, their graphs reflect about the line y equals x. When we change x and y, when we switch them, okay, we have that reflection about y equals x. Okay? Not something that is going to be like vital for what we're doing here, but the more understanding we have about inverses, the better. Okay. Now, last year in pre-calculus, you talked about it briefly, but we had a way of determining whether an inverse actually existed or not. Okay, so not all functions have an inverse. There are only special functions that have inverses, and there was a way for us to tell by the graph whether that was going to happen or not. So I'll give you about 30 seconds to brainstorm if you can remember how we did that.
Maybe if it's like a...
All right, I'll open the floor up because I know that this is something that may not have stuck with you. Like I know it was minor. Does anyone think that they remember? What? Nicole says like the horizontal or vertical line test. Which one? What does the vertical line tell us? If it is a function. The horizontal line tells us if it has an inverse. Okay, so would this function, does this function have an inverse? No. It fails the horizontal line test. If we were to reflect that, it would not be a function. All right? If we were to actually graph its inverse, which it doesn't have, it would not be a function, and so it's not going to work. Okay? What about something that looks like this? Does that pass the horizontal line test? Does that pass the horizontal line test? Okay. These two, the second and the third graph, would pass the horizontal line test, so they would have an inverse. Okay? Now, what if we don't have the graph? How can we tell? Okay, we can actually use calculus to do this. Yes, you can. Okay. So we call these two functions one-to-one. Okay? You may have heard that in pre-calculus, like for one moment of one day. Okay? A function is one-to-one if it passes the vertical and the horizontal line test. It's a function and it has an inverse. Okay? There's one x to one y, one y to one x. Okay? So we know that a function has an inverse if it's one-to-one. Now, we also know that if a function is one-to-one, it is what we call monotonic. Okay? So I want you to write down this number 2. If a function is strictly monotonic on its entire domain, yes, I'll tell you what that means, then it's one-to-one, and therefore there is an inverse. You know what I'm going to do? I want to see what you come up with for monotonic. Talk at your pod. You guys know English.
I feel like because Y's don't repeat. For every x value, one.
Maybe it's like if it was like x cubed, it's like x is one number. Oh, that makes sense.
All right, this is what monotonic means in terms of a function. If a function is monotonic, it is either always increasing or it is always decreasing.
Kind of close.
Kind of close? No? Okay, let's relate this to derivatives. If we are always increasing, what does that mean? The derivative exists, and it would be, if we are always increasing, our derivative would always be positive. Or, if we are always decreasing, then our derivative would always be negative. So if we can take a derivative of a function and determine that it's always positive or always negative, then we can say, all right, this function is monotonic, so yes, it has an inverse. Okay? Okay. So we're going to do 2 examples of that, and then we'll get to our rule. All right? I'm going to do this one first, I think. I'm going to go out of order. So that's okay. Write this one down. Okay, so for one thing, there's no way that we are going to be able to graph that thing without a little bit of effort, right? However, taking the derivative of that function is not that much effort for us anymore, is it? Like, you see the power rule and you're like, okay. So we want to know if this has an inverse. Let's find the derivative first. Our derivative. Caitlin, what is it?
3x.
Okay, so we need to determine, is this derivative always positive? Is this derivative always negative? Or neither one of those? 5 seconds, turn to your neighbor. All right, 5 seconds are up. Autumn, always positive, always negative, or neither? Autumn says this is always positive. Colby, why is it always positive? How do we know that this is always positive? What gives it away? Okay, so all of our y values are shifted up one, right? No matter what we plug into x squared, it's going to be what kind of a number? Positive times a positive number plus a positive number. That's always going to be positive, all right? So since our derivative is always positive, this is always increasing, which means monotonic, right? So f of x has an inverse.
So it depends on like what I was thinking about it is like we had some graph derivative.
It's always above the x-axis.
Right.
So it's always positive. I understand that. But since the derivative is always positive, our function is always increasing. That's what we care about. Okay? Did everyone hear that? Colby was a little bit stuck. He was thinking about that parabola. That is not always increasing. That's not what we're looking at. We're looking at our derivative graph is a parabola above the x-axis. And since our derivative is always positive, our function f of x is always increasing. And that is what we care about. Okay? Let's look at this example here. Does this guy have an inverse? Okay. Now this one may not take as much effort for us to graph, but that's fine. Let's at least talk about the calculus. Okay, Aaron, what would our derivative be?
2x plus 2.
Okay. Is this derivative always positive? Is this derivative always negative? Or neither? Okay, neither. This line is sometimes positive, sometimes negative. So this is not monotonic. So there is no inverse. Okay? We actually don't need calculus to tell us that, because what is our original function going to look like? It's going to look like a parabola. Is that parabola going to pass the horizontal line test?
No.
No, there is not an inverse that exists. Our derivative can be positive, can be negative. Not monotonic, we don't have an inverse. Yes, Cole? Are you sure? Okay. All right. The most important thing you write down today. Ready for it? Okay, I know it's a rainy Tuesday, but let's do it. The derivative of an inverse. The derivative of an inverse. And what you're going to see is we're going to really just worry about this at a coordinate because that's going to be about the only situation we're going to be able to do it. Okay, now what I'm going to do, I'm going to show you why this rule is the way that it is. Just watch because it's a good reminder for some of the rules that we talked about, but I don't want you to write it down. I just want you to watch me do it. Okay? So first of all, the inverse derivative is 1 over f prime of f inverse. So we need to know information about f in order to be able to find its inverse derivative. Okay, which is why we're really going to do this at more of a coordinate. Okay, so first of all, what do we know about f composed with f inverse? What do we know about that? When we compose a function with its inverse, it equals x. Okay, we know that. So I'm going to take the derivative of both sides. All right, what's the derivative of x? That was nice, right? Okay. What about the derivative of a composition? Oh, we know how to do that, right? We know that we're going to take the derivative, keep the inside alone, times the derivative of the inside. So, f inverse prime is just 1, and then we can divide over what's being multiplied to it. F prime of f inverse. That is why this rule is a rule. Okay? This is what you need to remember. Okay? It will be a question on your test.
What is that?
Like, what's the derivative of an inverse? Bam, there's your answer. Okay. So the remainder of our time, I think I have like 3 problems that we're going to go through. Okay? But you are not going to stay in your seat. More than likely. Okay? If you are the tallest, if you are the shortest at your pod, stand up, find a different seat. You have 20 seconds. Oh, there's only 2 of you. Both of you. Just anywhere. Just find a new seat. If you're the tallest or the shortest, just find a new seat. I'm just trying to mix it up a little bit. Here, pod 4 needs somebody.
Where did Nick go?
Well, there was only 2 people on this pod, so they both had to switch it up. Okay. Please write this down. Nice and bright.
Why just
Okay. If we want to find f inverse, are you done? All right, let's put it back in there. F inverse prime of 3, then we need 1 over f prime of f inverse of 3. Right? That's just the rule right there. but I just put a 3 in instead of x. Okay, so now we need to figure out all of this information. Okay, so our first task would be to figure out f inverse of 3. That's the inside, right? F inverse of 3. How do we do that? If we know our function, how do we figure out the inverse evaluated at 3? We don't have to find the inverse to do it. Aaron, you have an idea?
So you plug like 3 in for x, and then that would be like the y value. And it's like if like you over the line y equals x, then you'll have like your x value for the inverse function.
Okay. So what you just said, I'm gonna go with that last part you said. Like whatever you have on your function, when you reflected about that line, whatever your y value is becomes your x value for the inverse. Okay. So if our x value is 3 for our inverse, what does that mean about our original function? 3 would be for the y value. Okay. So we need to figure out which x value makes our y value 3. And you can use some guess and check here. I have no problem with that. What x value can we plug in to make it equal 3? Obviously, 1's not going to work. What's 2 cubed?
8.
Divided by 4. Plus 2. Minus 1. Okay. So what we just decided, if I plug 2 into our function, we get 3. Do we agree with that? If we plug 2 into our function, we get 3. Which means, if we plug 3 into our inverse, we should get 2. All we do with inverses is we take x and y and switch them. Okay. So let's come over here. We are now looking at, we know that f inverse is 2. Look at that fraction. 1 over f prime of 2. Ah, do we know f? We know f is 1/4 x cubed plus x minus 2. Can we find its derivative? Yeah. Okay. The derivative of f would be 3/4 x squared plus 1. So, f prime of 2, let's plug it in. When we plug in 2, what do we get? We get 4, so since we have 1 over it, we have 1/4. Okay. Not a lot of tricky derivative that we need to worry about. It's more putting all the pieces together. So first thing, you have to remember the rules. 1 over f prime of f inverse. Okay? We got to figure out what that inverse value is so that we can plug it into the derivative of the original function. Okay? Questions on this example. We are going to do 2 more, but questions on this example. All right. If you are wearing red or green or blue, like on your shirt, find a new seat. Dig pink people, you're safe.
Oh, yeah, okay. This is that crimson shade. I'm a fan.
Give a blue sweatshirt. All right, I just want to get you moving around, sitting by different people. Okay? Go ahead and write down this example, please. What is exciting about this example? It's natural law. That's exciting to the Turner. There's something that I'm giving you that in this example that I didn't in the other one. I gave you the entire coordinate, didn't I? All right. So what does this mean right here? What does that mean? Is this on the inverse or the function? The inverse, right? Find the derivative of the inverse at 7, 1. So this means that our function at 1 equals 7 because we would have to switch the x and y for our original function, right? Okay? F inverse of 7 equals 1. That's what that means. Okay? So if I want the derivative of the inverse at 7, we are looking for the inverse derivative at 7, which we know is 1 over f prime of f inverse. Okay? Well, guess what, people? We know what f inverse of 7 is because they gave it to us. F inverse of 7 would be 1. They gave you the y value. Okay? So now all we have to do is figure out f's derivative so we can plug 1 into it. Okay? At your group, find f's derivative, please. What is that? It's like 3. Oh, it's 1 over. Okay, our derivative. Our derivative. Okay. Grace F, what you got for me?
21x squared plus 3 times ln x.
Okay, 3 times what? squared. Okay, this is Grace's derivative. 21x squared. Okay, that wasn't the challenging one, right? Here, we have to do the power rule, and then times the derivative of the inside 1 over x. Okay? Now, we need f prime of 1. What's the natural log of 1? 0. Okay. So since f prime of 1 is 21, then our inverse derivative at 7 is 1 over 21. Okay. What do you think? What's the first thing you have to do in both of these problems? What did we have to decide? Both times, we had to first figure out what the inverse value was. In this one, we had to figure it out. In our second example, it was given to us. Okay? We first have to figure out what our inverse value is. Then we have to find the derivative of the original and plug that value into it. Okay? So one more time, let's mix it up. Whoever has the longest hair, whoever has the shortest hair, find a new seat. Okay, so at the pod that you are now sitting in, please work together to find me the inverse derivative at the coordinate 2, 0. Oh, the coordinate 2, 0. That was nice.
I know.
So since we're at the coordinate,
The derivative of
Yeah, we put in 7 for that one.
okay.
we can wait the f the inverse. So f at
Zero
Yes,
is
1 over f prime of 0. Yeah, so now I just got to figure out f prime of 0. What I like when you run f prime of 0.
okay, yeah.
This means on your inverse, your y value is 0. So your inverse, your y value is 0, which is why you have f prime of 0.
Oh yeah. My brother's girlfriend. 2 hours. You might have
Okay, let's talk about it. Do we all agree with what I have written up here? Okay. Autumn, what is F? Oh, I've already picked on you today. I'm not going to pick on you again. Jesse, what is F inverse of 2? Okay. Tegan, how does she know that F inverse of 2 is 0? Yeah, because of the coordinate, right? We have a coordinate 2, 0. If we only had 2, how would we find 0? Okay. We would have to figure out which x value made our function 2, so then we could switch it for our inverse. Okay? But we didn't have to do that. Hooray. Right? Alright. So then f prime of 0. F prime of 0. Mandy, what is f prime?
Negative 3x squared minus 1.
Okay. And when we plug 0 into that, we get negative 1. So we have 1 over negative 1 is negative 1. All right, go back to your seat.
No balls. No balls.
Okay, so your homework tonight, you have 6 problems. 6 problems. This is probably one of your shorter assignments all year. Okay? I don't think they have Oh, okay. Colby brings up a good question. Is this always going to be guess and check? So when we were over here at this example, we sort of had, we had to guess and check for our value. The reason we did that is because we had a cubic, and we don't really have the tools to really take the time. I mean, we could solve it eventually, but we want it to be a little bit quicker. If this were a quadratic, you could set it equal to 0 and factor, but since it was a cubic, we just did some guessing and checking to make it go a little faster, okay? But if you had a quadratic, set it equal to 0 and solve, that would be easier than trying to guess and check. Yes?
Couldn't we just add 1 over and then take out an x and then...
You can only do that if it's set equal to 0. We can only factor if we're equal to 0, because the only property that we know for sure is something times 0 is 0. Okay? If you were to add that 1 over, there's lots of ways we can multiply to be 4. We could have 2 times 2, or we could have 1 times 4, or all sorts of different things. Okay? Other questions? Eli, did you have a question, or were you just... Okay. Tomorrow we are going to have a notes sheet, so if you know you're going to be gone tomorrow, I can give that to you now. And then, like I said, we'll be doing some AP work Thursday, Friday, and reviewing for our test Tuesday, Wednesday. Okay? You're gonna be gone tomorrow? Yeah.
So my quiz is in the gradebook isn't complete right now. So
Yes, because it's right here. Since you took it at I left after school Friday.
I was just. Is it graded or not?
It is not.
Okay.
You would.
I was
you would
just
see
wondering.
if you just have it here.
Yeah, she actually gave you 0.
So what I'm gonna